Recording started. Okay, so welcome everyone in the week 5. So welcome to this course biochemistry, and in week 5 we ma'am had discussed enzyme inhibition kinetics and the enzyme catalytic mechanism. So I will be discussing the problem set on that particular topic, and then I will also be discussing some of the problems that students have texted me through WhatsApp in the WhatsApp group that they want to have the clear idea on ionization pKa, then thermodynamics related problems and the spectroscopic properties of amino acid. So is- mm, stay till the last of this lecture. I will be discussing those all topics in the end of the session. So before I will discuss the problem set of week 5, which is enzymes continued. Enzymes started in week 4. So I am Karan Kumar, Senior Research Fellow at IIT Guwahati. This is my website for more information, and you can email me anytime at karan18@iitg.ac.in. These are my other professional handles: LinkedIn, ResearchGate, Google Scholar, and YouTube. You can click any of the link, and then you can navigate to my like this course YouTube channel. And so let's come to the content of this presentation. The topics that were covered in week 5 in the NPTEL portal, that was enzyme inhibition and inhibitors. Then the different types of enzyme inhibition and their effect on the reaction velocity and the Km value, Michaelis-Menten constant for a single substrate reaction. Now the various different inhibition types such as competitive, non-competitive, uncompetitive, mixed and feedback inhibition. Later on, ma'am talked about the different mechanism of enzyme catalysis, and she specifically talked about the lysozyme and ribonuclease A. Then she also gave a brief idea about allosteric regulation. So I will be asking few questions based on that particular uh, topics itself from these 7 topics, and then I will, in meantime, I will also I will also discuss the problems that you are facing, and also I will tell how to solve this problem approach. So before that, I would like to know, because you have completed the enzyme inhibition module, so can anyone unmute themselves and uh, attempt this question? The first one: what do you understand by enzyme inhibition? What do you mean by enzyme inhibition? Anyone? How many are there? Okay, only 2. Yeah. So any idea about this? What is enzyme inhibition? Anyone? 3 or Gayatri, you can, and any one of you can unmute if you want to answer for this question. As this is interactive session, so I want you to interact with me, and then it will be helpful for your understanding itself, understanding only. Am I audible? Okay. So enzyme inhibition terminology, that means here normally enzyme or any protein, they act on a specific substrate. And this is true for all biochemical reactions that happens in our body or any microorganism. For enzyme catalysis, enzyme means it will catalyze a particular kind of chemical or biochemical reaction. And for that, the reaction catalysis means it will have the involvement of substrate, and production will be there is a production of a particular specific product, that is your product of interest. Okay, so what enzyme do? It lowers the activation energy and it helps in achieving the transition state much earlier, and in meantime the reaction time is reduced. It is very much helpful in producing a specific product also, minimizing the non-specific products. So what is enzyme inhibition? Enzyme inhibition means in some of the reactions or metabolic reactions as per se we are talking about, in metabolic reactions such as when a particular cancer, let us talk about cancer. Okay, a particular cancer is progressing through the metabolic some kind of inhibit, like it is progressing through some metabolism, and you want to target uh, its metabolic pathway in a particular enzyme, because in that particular metabolic pathway there will be a set of enzymes, and targeting this particular enzyme only, the let us say there are in a cancer tissue or in a cancerous cell, there are in its metabolic pathway there are multiple enzymes, one, two, three, four. So let us talk about only four enzymes. And in normal cells also you have similar set of 1 prime, 2 prime, 3 prime, and 4 prime. Okay, and you want to study if you want to stop the progression of this cancerous cell. Okay, you want to stop the progression of this cancerous cell, and you understand that you can do using inhibiting a particular enzyme. So for that, the inhibition means if you stop at the 2 itself, it will not progress and the energy won't be produced and cancer cell dies. That is the main motto of inhibition. Means you can use by the means of drug, or so inhibition can be beneficial or it can be detrimental. In beneficial in sense, if you want to design a drug, drugs are mostly kind of inhibitors, or it can also act as a regulator in your cells, in organism. How it is happening? There will be a specific type of enzyme which will be catalyzing a particular reaction, or it will be it is therefore it might be responsible for binding of or sensing a particular sensing a particular kind of a biomarker, or and then it will do the signal transduction in the cell, and that may progress a particular disease, that may be the cause of a particular disease. So what you can do, you can mimic this particular substrate using your drug. You can have the similar kind of structure which is responsible for the if this interaction of this small molecule with the enzyme, or a or what you say enzyme or any receptor molecule. So what you can design in your drug, that both of these interacting site are kind of similar, and that in that sense what this particular enzyme or this particular kind of receptor will think that it is their substrate only, and but these are not the substrate, or these are not their small molecules that they need to bind. So there how it either it can interact, either it can completely block this channel so that the sense molecules cannot bind to this sensor and the progression will not happen, or it can reversibly or irreversibly it can bind in both manner. So that is how your drugs are being made, and that is what your functioning of drug is. So that is inhibiting a particular role of enzyme or a protein is called as enzyme inhibition. Why understanding inhibitory effect is so much important? Because once you understand the inhibition mechanism, once you understand the inhibitory effect in a particular enzyme or in a particular metabolic pathway or in a cell or in any system, reaction system, then it will be so much helpful for you to regulate that particular reaction. If you want to stop that particular reaction, you can design the you can design that particular molecule using chemistry techniques, and then you can finally dock that molecule with your receptor or enzyme which is responsible for that particular kind of reaction. So that is why the this enzyme inhibition is so much important to understand. That this will give you a lot of opportunity to regulate your reaction of interest. Now, what is the scope and topic scope of this topic with research perspective? This technique is used in much of the pharmaceutical industries. Like uh, for designing a drug, either you can or if you are trying to understand the role of a particular enzyme, this will help you a lot to unraveling the mechanism also. If you understand, if you know that in your system there is an enzyme A present and you don't know much about the action mechanism of this enzyme, what you will do? You will do the docking analysis in which you will bind your drug molecule or your substrate molecule or your analog to this enzyme, and you will study how the inhibition kinetics or how the mechanism is favoring, like which all amino acids are interacting with your substrate molecule or which all amino acid residue are kind of participating in catalytic activity. So this is very much important in understanding the catalytic mechanism. So these are used in catalytic mechanism. Designing vaccine, designing vaccines, then designing drug molecule, or this will be also helpful for you to regulate your reaction system. Okay, so what type of questions are asked in GATE and CSIR-NET examination from this topic? You will find a lot of questions, at least in any paper, whether you are attempting GATE or you are attempting CSIR-NET, you will find at least 2 questions from this topic, at least, and at most it can be any number, but at least 2 questions you will find in any exam, like any GATE exam or NET exam, and you find any sample paper, you will see that the question coming up in all entrance exams. So be prepared for this topic. Uh, Now, based on the concepts that were covered in week 5, I have designed some of the questions. Try to answer this question. Your first question is, in case of protein ligand docking, dash ligands are often in adapting their shape to fit the receptor binding pocket. So options are large molecule and highly flexible, small molecules or highly flexible, large molecule more flexible, and small molecule less flexible. What will be, can you guess this? And for a disclaimer, ligand can be anything. Ligand is the analog to any sub. Like ligand can be anything. It can be inhibitor. It can be substrate for that particular enzyme, or it can be a product. Anything that can bind with the protein, that have the uh, interaction with the protein or enzyme. These are known as the ligands. Okay. So, and you will find this terminology as much general when you understand, when you are studying the protein-protein interaction, protein ligand interaction, or protein small molecule interaction. You will find this terminology everywhere. So that is why instead of writing enzyme substrate, I have written protein ligand docking. So can somebody answer this question? Unmute themselves. Anyone? Anyone? Sakshi, Abhilasa? Okay. If not, then yeah. Let me clear this out. Here, in case of protein ligand docking, protein or enzyme. These are termed as the macromolecule because they have, sorry, because they have many number of atoms in their structure, and these are the kind of like the protein can have the protein or peptide can have the amino acid number from 10 to thousands of amino acid also in their structure, and in one amino acids there are at least 20 to 30 atoms. So in that sense, if you understand that protein will be kind of a large molecule, that is why it is called as a macromolecule. However, ligands, because these contain only few atoms, these will be termed as small molecules or macromolecules, micromolecules or micro, because they are smaller in size. So in case of protein ligand docking, ligands which are small molecules are often in adapting their shape to the fit receptor binding pocket. So option B is correct here. If let us say there is a large molecule, if say this docking or enzyme substrate binding is normally described by the two con- uh, two broad theories, which is induced fit and second is lock and key. There are two mechanisms, lock key mechanism. So how do you understand this lock and key mechanism? In lock and key mechanism, what was proposed that both the enzymes and its substrate will be complementary to each other and they will have the rigid structure. How you find a lock in your house? Your locks are rigid, and based and your keys will also be having the complementary structure to this particular lock. Then only this lock will open. Similarly, in enzyme substrate kinetics, the same thing was proposed that to catalyze for every substrate, there are a specific enzyme which can catalyze that enzyme, which can catalyze that reaction, and in that sense, in lock and key mechanism, both enzyme and substrates are rigid. However, this was not true. This was not always true because when the crystallography structures were studied, when the protein were made crystal and then X-ray crystallography was studied, then what they observed that proteins are not kind of a rigid structure. First of all, they are very dynamic, and also because of the many different types of amino acid present in their structure, they have the different properties, different, and they can, based on the environmental condition, they can reshape themselves. Okay, so the X-ray crystallography suggested that proteins are not rigid, and if there was a lock and key mechanism, then what would happen? Only one particular substrate will be accessing to a particular enzyme, but that is not true. What do you feel? Like in some of the enzymes, they can catalyze their analog also. So if it is specific to a particular substrate, that uh, then this case will not be true. Then they can also catalyze the analogous of that particular substrate. So then the scientist again proposed that there is one more model they proposed, which was the induced fit. And in induced fit, what they proposed, that enzyme will have a particular structure, but when its substrate will come, then it will dock to its complementary structure, that is lock and key. But enzyme has particular structure, but when in this vicinity, when one substrate will come which shape is not complementary to it, it is not complementary to the enzyme active site or binding pocket, then what will happen, enzyme will restructure itself, and again it will make a kind of a cavity where this particular substrate can bind and can have maximal possible interaction. So in this theory, in induced fit theory, enzyme was treated as flexible. Its structure was not rigid, and that was suggested due to the in X-ray crystallography or NMR techniques, that enzymes or protein don't have rigid structure. So the answer here is small molecule, and these are highly flexible. Okay. Next question is, which of the following is true regarding the protein flexibility? Okay, as I have discussed here, the protein flexibility, because the chains are flexible. So based on that, one question is, which of the following is true regarding the protein flexibility? Option A, method have been described for the introduction of side chain flexibility for both protein ligand and protein docking. Protein docking. Methods have been described for the introduction of side chain flexibility through protein ligand docking only. Option C, the mean field principle is rarely used in this. And option D, methods have been described for the introduction of side chain flexibility to the protein docking only. Any guess? Who all are here? Okay, any guess? What could be the possible answer for this question? Okay. So here, what I talked about the protein flexibility, in this, the methods that have been described, these are for the introduction of side chain flexibility. The only thing that can be flexible in the protein is the side chain, because normally proteins have a rigid backbone, and that backbone has some structural constraint. So while making the protein as a rigid, only which the random coils and the side chains that have the flexibility in the both protein ligand and protein docking. Okay, so the protein flexibility is true regarding that the methods that have been described for the introduction of side chain flexibility, and which is for the both protein ligand and protein docking. Now the next question is regarding the allosteric interaction. Okay, your question is, an allosteric interaction between the ligand and protein is one which, option A, binding of a molecule to the binding site affects the binding of additional molecule to the same site, or binding of a molecule to a binding site affects the binding properties of another site on the protein. Option C, binding of the ligand to the protein is covalent, or option D, multiple molecules of the same ligand can bind to the same binding site. What is the allosteric interaction? Anyone?
So option B.
Option B?
Yes, sir.
Binding of a molecule to the binding site affects the binding properties of another binding site to the protein. Very good. These are termed as the allosteric interaction. And similar, by if it is operating in a positive manner, then it will be kind of a allosteric in positive sense, which is also called as a positive cooperativity. And if this interaction is inhibiting, then it is called as a allosteric inhibition. Okay, and if it is on the positive side, then it will called as a allosteric activation. Okay, and can somebody give me the example of allosteric activation? Anyone? Let us say uh, there are two binding sites in a particular protein. If this particular molecule bind here and it activates the binding of this, what kind of situation it will be? Allosteric activation or allosteric inhibition?
Sir, will it help in binding of another molecule?
Yeah, it once this particular a molecule is binding to its binding site, and then it is opening up the active site of this so that the B can bind. So which kind of it will be
Activation.
activation? Yes, very good. And this is also sometimes termed as the cooperativity, which is which you see in the hemoglobin binding, oxygen binding of the hemoglobin molecule. Now the next question is regarding the plots that you have been studied. So the question is, when the binding data are analyzed in scattered plot, the slope is used to estimate this, and the x-axis intercept is used to estimate this. I will also talk about what is the scattered plot, because you might have studied the Lineweaver work plot. And then the different like Maclaurin-Menten plot. And this is also known as the double reciprocal plot. So the scattered plot is similar to the Lineweaver plot, but the difference between the scattered plot and Lineweaver plot is that when you are studying the enzyme kinetics, then you term this as the Lineweaver plot. But when you are studying any protein or ligand interaction, these are termed as the scattered plot. Okay, so can you tell me the slope is determined for which purpose in Lineweaver work plot? What you can analyze in the Lineweaver work plot? KD here, KD is the nothing but dissociation constant. KD is dissociation constant, and binding stoichiometry is the how much binding is happening in this particular binding site. Okay, so now can you tell me what will be the x-axis intercept in Lineweaver work plot? Here in the
concentration.
yes, substrate concentration, right? In the x-axis of Lineweaver work plot, that is the inverse of substrate concentration, right? But what will be the intercept of that particular x-axis? What you will find in is like Lineweaver work plot, if you are plotting, and then you are in the x-axis intercept, what do you get? Answer here is you get the KD value on the slope, and on the x-axis you get binding stoichiometry. let me show you what are the what is the scattered plot. Let me show you. See, this is the scattered plot. So in scattered plot, how it is assumed that let me take a free slide. Is it visible to all? Are you able
Yes,
to
sir.
see my screen?
Yes,
Okay.
sir. Yes, sir.
So what is scattered plot actually? The scattered plot is normally in enzyme substrate binding, you study enzyme plus substrate, giving you the enzyme substrate complex, and then finally you get the enzyme end product. But when you are studying a protein ligand means when you are studying the interactions, such as when you are inhibiting your particular protein using inhibitor, then in that case you don't get any product out of it. But there will be, when you will be studying that particular inhibition kinetics, then you will need the binding of this kind of scattered plot curve. So in the scattered plot curve, what you what you do, like let us say if we are inhibiting it using the inhibitor, it will give you the ei complex. Okay, but this ei will not dissociate and it will not produce any kind of product. It will just have a interaction with the enzyme, and this is what known as the protein ligand docking. Now if here in the ES also, this is protein ligand docking, where ligand ligand in this case means the inhibitor. However, in this case, ligand means substrate. So when you are studying the binding properties of a particular substrate or inhibitor or any compound with the enzyme or protein, then you plot scattered plot, and this is scattered plot in which the y-axis is. And how do you study? You study using the fluorescence spectroscopy. So in the fluorescence spectroscopy, what happens that there will be a kind of a, like one protein is there, one protein P. If there is one protein, then it will have the like amino acid residue such as tryptophan, aromatic amino acid residue, which can which can absorb light. Okay, which can absorb light in UV range, and some of the light can also transmit while coming, like how it is observing. I will tell you the this basic of fluorescence spectroscopy is that you the in your in your system there are molecules. So these are the protein molecules. Okay, and in the tryptophan residue, the electronic state in the ground state level, when you excite them using the UV light of a particular wavelength, which is UV light in 280 nanometer, because at 280 nanometer they absorb light, right? So from ground state G, when they absorb this light, they go to their excited state E. This electron will jump to its next excited state level, like it, because it will absorb only those that much light which is in the quantum packet h nu. Okay, so that it can jump from the one level to another level. And if the packet is not complete, like if the energy level are not like energy supplied is not in the uh, correct amount of energy gap, then the transition will not happen. Okay, so when 280 nanometer light is excited on this tryptophan residue, the electrons in the pi electrons that are there in the delocalization, they they absorb this energy, and make a transition to its excited state. While coming back, when it will make the transition, that is the UV absorption. But this electron will not forever stay in this particular excited state, because excited state is the higher energy level, and all electrons or any kind of system, electronic system, it need to come back to its ground state again. So during the when it is coming back to the excited state, when it is coming back to the ground state from excited state, it emits some light in the meantime. Okay, which is called as the fluorescence, and that is what is observed in the fluorescence spectroscopy. Now, while making the transition from ground state to energy state, like excited state, their wavelength was 280 nanometer, like it is in the UV range. But when it is coming back and it is also emitting light, so this light emission, this particular is the wavelength that it will emit, it will not be having the same energy, because the whole energy is not complete, right? So in that sense, the like energy will be less. Less energy means higher wavelength, right? So you will see the light in the visible region, and that is why it is called as a fluorescence. Like your some molecules with fluorescence. Fluorescence means you can see that by the naked eye, or some of the time it is not visible. Okay, if it is in the visible range, which is 400 to 700 nanometer, if the energy of this particular light is in the range of 400 to 700 nanometer, then then you can see through the your naked eye, because our eye can see this light in Vivier electromagnetic spectrum from 400 to 700 nanometer. Our eyes can see this light. So when a particular molecule is emitting light, when a particular molecule is emitting light from while coming from excited state to ground state, then you can see that light as a fluorescence, which is observed in fluorescence spectroscopy. Okay, so uh, this scattered plot principle is based on that. Let us say there is a protein molecule. It has two tryptophan residues in its structure, two tryptophan residue W. And once uh, uh, if protein is not bound with any ligand, then this there will be a particular kind of spectrum, like fluorescence spectrum. You will see a particular kind of fluorescence spectrum. But when it is bounded with ligand, now this protein is bounded with ligand, and this ligand will have some interaction with the tryptophan residue, and which is in the active site of that particular amino acid. If this tryptophan is in the binding pocket of that particular protein, and that this tryptophan is interacting with this small molecule, then the fluorescence will reduce. That is what you have understood from the like the spectroscopic technique, right? Because if it is not bound, then it will emit some particular wavelength, and if it is bound with a particular compound, it its fluorescence may be reduced or enhanced somehow, based on the changes that this particular small molecule is imposing in this tryptophan residue, or in like similar fashion, right? So thereby you will see some change in either decrease or increase in the spectral like observation, right? So this is what you observe in what your fluorescence spectroscopy. In most of the time, this fluorescence is being quenched, which is called the fluorescence quenching. Means now the light which is not which was emitting the this intensity which it was emitting is not equal to when it is docked with a particular ligand. This is what we monitor in fluorescence spectroscopy. So if the fluorescence is reduced, then that means the protein is bound with that particular ligand. And this so here in the y-axis, what you observe, that is the bound residues divided by the free residues. Okay, on x-axis you you get the how much fluorescence you are getting, B max. Okay, so scattered plot is the inverse of this, and you will see KD, which is the dissociation constant on the y-axis, and in the plot you will see it will be the inverse of KD. Okay, which is inverse of K. K is association constant, binding affinity, and KD is the dissociation constant. Means the molecule is dissociating from is the interaction. Is it understood? Now everyone understood what is the scattered plot, and normally it is used in understanding the protein ligand interaction. Okay, I will show you the equation also. So this is the scattered equation, where R by L is the ratio of ligand bound and free protein. Okay, and in the x-axis intercept you will find N. This is N is the number of binding site. Minus K is the slope. Okay, minus K is the slope. So inverse of the K will give you KD, right? So in the slope you will see dissociation constant, and in the intercept of x-axis you will find the binding affinity, like binding stoichiometry. Okay, so the correct answer here was option. Your correct answer was option. Which one? Option A, which is the slope will give you the KD, and x-axis intercept will give you the binding stoichiometry of that particular protein. This is how you also analyze how much oxygen molecules are bound to the hemoglobin, and similar techniques. So this is for used, scattered plot is used for identifying the protein ligand interaction. Now the next question is the mechanism of lysozyme cleavage. You have ma'am has discussed the lysozyme catalytic mechanism, right? So in the lysozyme catalytic mechanism, you will find the two amino acid residues that plays an important role in catalytic activity. Okay, which is glutamine 35 and aspartic acid 52. So here the this superscript denotes at which position the aspartic acid is present. Okay, so in the lysozyme protein, there will be a multiple amino acids at the different position, right? So aspartic acid at 52nd position and glutamic acid at 35th position. These two amino acid residue plays an important role in catalytic site of the lysozyme. Okay, so the question is the mechanism of lysozyme cleavage of polysaccharide substrate, which is NAGNAM, in its non-ionized form, whereas nearby aspartic acid must be ionized. Okay, so the pKs for this side chain carboxylic group on the two amino acids in the solution are virtually identical. Okay, now the question is how can one carboxylic group be charged and another be uncharged in the active site of lysozyme? If both of, let us say there is a lysozyme, and in this lysozyme the two amino acids are present, which is glutamic acid 35 and aspartic acid 52 in the close proximity, and this is present in the common solvent, right? The solvent will be the common for both of the amino acid, but how it is possible that because glutamic acid also contains carboxylic acid, aspartic acid is also containing carboxylic acid in the structure. Then how can one carboxylic acid is charged and while other is uncharged in the active site? Can somebody explain this phenomena? Another question is the the pH optimum for lysozyme is about 5. Okay, then why do you see that there is a decrease in activity below and above this optimum? Means if you are changing the pH to 7 or if you are changing the pH to 3, then why do you see the decrease in activity of this particular lysozyme enzyme? What is the mechanism? So anyone want to attempt the question number A, 5A? How it is possible that one of the carboxylic acid of the amino acid residue is charged and another is uncharged? Anyone? Normally this kind of questions are asked in GATE examination because there will be a factual question there, but in some part of it, if any one of you are have already attempt CSIR-NET examination in part C, normally you will find a logic based question. So if you just mug up the theory, it won't help you to solve the problem. So you need to understand the basic and fundamental of it to answer these kind of questions in the competitive examination. So try to think about it. Why in a particular system, if the both amino acids are present in the active site, then one is charged and another is uncharged. How it is possible? Can somebody tell me? Anyone? Any idea? Yes.
Sir, regarding option B, I think since the lysozyme will act on the optimum pH, so decreasing the pH or increasing the pH will affect its activity since it has a
Hmm.
specific optimum pH. Every enzyme has a specific optimum pH. On
Yes.
option A, I am not able to understand it.
No, option B, it is given in the question itself, right? The activity decreases. But I want to understand why, what is the mechanism? Because you have already understood now how lysozyme is operating. In the first time, the glutamic acid will be charged and then it will act on the like this glycosidic bond and it will break. But what actually happens are like at above and below of the amino acid, at above and below of this optimum value? Activity will decrease, that is already given in the question, but what is the mechanism? Now you have already understood the mechanism, then try to think about it in the pKs value. I am giving you the hint. It has to deal with the pKs of the side chain.
So,
Any idea? Both of the aspartic acid and glutamic acid are the like carboxylic acid containing group, right?
yes, acidic amino acids.
Acidic amino acids, right? So
Yes.
the answer here is, let me give you the answer for for B first, because you have already attempt this. So let me give you this. So normally when the pH drops, okay, if you see the side chain, like because most of the like amino acid, if you see the structure of like let me open up the structure of glutamic acid and aspartic acid both, so that it will be helpful for you. Glutamic acid. This is glutamic acid and now aspartic acid. Okay. So this is the structure of aspartic acid. Now, now what you have studied? This glutamic acid has one more carbon chain. The chain length of the carbon is one greater than the aspartic acid, right? Due to which there will be a some kind of a hydrophobic character, right? And that helps in like increasing the like this aspartic acid's pKa value will be lesser than this one. Do you agree with this? Do you agree with this comment? That the pKa value or the side chain pKa value for aspartic acid will be lower than the glutamic acid. Do you agree with this? Are you agreeing on this?
Due to its
Because
extra.
extra carbon will introduce the hydrophobicity, which will have the impact on the acidity of this particular acidic amino acid.
Yes, sir.
Because as you increase the carbon length, the polar nature will reduce, right? As you increase the carbon length, it will be more kind of non-polar. But both are the in comparison to the aspartic acid, in comparison to the aspartic acid and glutamic acid will have higher pKa value than the acetic acid, right? Because it has aspartic acid has the lesser carbon chain like carbon number,
Yes, sir.
this CS3, right? So what does it impart? The pKa value will be lower for the side chain of aspartic acid, and
Aspartic
for
acid.
glutamic
Yes.
acid it will be higher. So what
Yes.
will happen? What will happen? Because to operate both amino acids at the same like in the same active site, the pH is important. Now, when the pH drops, then what will happen? The aspartic acid, which needs to accept the proton, won't be able to accept. Okay, and it will be in the case of non-ionized form. Okay, I have put up that slide in the mechanism. So this is this is the aspartic acid. This is the lysozyme catalytic mechanism. So to operate, because in the first step itself, this glutamic acid will act as a acid, right? It will donate the proton. But when but when there is a drop in pH, what will happen? This glutamic acid will not be able to be ionized, and the aspartic acid, which is lower pH, it will ionize first. Okay, because of lower pKa. If you are changing the pH to down, okay, if you are changing the pH to below 5 is optimum, because at that pH, aspartic acid will act as a base and glutamic acid will act as a acid. Okay, because it is donating proton, right? And
Yes, sir.
in the next phase, this glutamic acid, when the pH will change means it will only happen when water molecule will come, and this water, because this water is higher pH, because normal water's pH is around 7, like in the physiological range. And now when it is ionized, which when it contains the negative charge, in that case it will take the proton, it will act as a base, and then this will create the OH as a nucleophile, and it will attack on the chain, and there how you get the one monomer separated from the structure. Okay, so for catalyzing both of the amino acid, the pK value is must. That is why the pK concept of ionization and pK was taken in the second class, so that you can understand the mechanism properly, because all the catalytic mechanism, these has to do with the pK value. If you change the the pH, if you change the environmental condition, their pK value will not be the same. Their pK, the whole enzyme pK is 5. Like here, the optimum pH for lysozyme is 5. But all the amino acids that are there in the active site, the pK value for them is not same, right? So based on the environmental pH, they will act accordingly. That is why when the pH drops, then in that case aspartic acid will pick up the proton. It will not it will pick up the proton and will become ionized. Okay, and then this aspartic acid will interfere with the glutamic acid, and glutamic acid will not be able to act properly. And it will be the inverse in case of when you increase the pH. When you increase the pH, in that case, glutamic acid will not be able to ionize properly. And acetic acid will be in the like ionized case, aspartic acid. Okay. So in that case, when in the first case, glutamin 35 will be will become ionized and it will accept the proton, and in that case it will the first step itself is not being it's not being proceeded because this is ionized. When it donates proton, then only it will go into the negative charge. When you have increased the pH, glutamic acid will not be able to give away its proton, and then in that case it will interfere with the uh, this increase in pH will interfere with the catalytic mechanism. That's how when you change the optimum, this is why the optimum pH is important for any particular amino acid or any particular protein, because the catalytic efficiency depends on the pK value, and that's how the active site is able to catalyze a reaction. Is it clear to everyone now?
Yes, sir.
Okay, so that was the answer for your first part. Now for answer of your second part, that is already I have given in the second part itself. So because all amino acid side chain, they have the different pKs, which are not quite similar to what is there in the environment. Okay, so in that case, the environment will produce a non-polar condition for glutamic 35. Okay, so glutamic acid 35, the condition will be non-polar in which the ionization is favorable. So in that case, the one carboxylic acid, which is glutamic acid, that will be ionized, but that is inverse in case of aspartic acid. Aspartic acid will not be ionized at the optimum pH, which is pH 5, and therefore both will exist in the different charge. One will be in the charge state, which is glutamic acid 35, and aspartic acid 52 will be on the uncharged state because of it, because the side chain have the lower pK value than the aspartic glutamic acid 35. Is it clear? While I will be giving this while I will be giving this PPT, then
Yes,
I
sir.
will write the answer below so that in the future you will be able to understand what I talked about. Okay. Now the
Okay.
next question is the target substrate molecule. The target substrate molecule bind to the active site of the enzyme transforming into product through a series of steps. These are known as which kind of uh, process? Enzyme kinetics, enzymatic mechanism, chemical kinetics, or zero order kinetics?
Enzyme mechanism.
Enzyme mechanism. Any other answer anyone have? Or everyone is agreeing with the enzymatic mechanism? Any different answer? Okay. This process is known as the enzymatic mechanism. Now the next question is, the lock and key model deals with the flexible nature of enzyme. Is it true or false? I have just described false, right? Because lock and key model assumes that both are in the rigid form. The explanation is also given here. The lock and key model possesses as a key fits to the model, the substrate fits to the active site of the enzyme. This model does not consider the conformational changes during the binding of substrate, and which is provided by the X-ray diffraction and NMR. Now the next question is, which of the following is not true for the substrate collision theory? So normally substrate collision theory is given to understand how the reaction will progress. That is true in the chemical kinetics, and that is also valid in enzyme kinetics. So in enzyme kinetics, the substrate have to first stumble on the enzyme. Okay, so which of the statement that you think is not true for the substrate collision theory? Is not true. Option A, both enzyme and substrate stumble upon each other. Option B, both enzyme and substrate provide good molecular orbital interaction. Option C, specificity of the substrate binding site. And option D, both enzyme and substrate should be flexible in forming transition state.
So option D.
Option D,
Yeah.
the substrate should not be flexible in forming transition state. Any
So
other answer? Anyone else? Here your answer is incorrect, because the substrate, like substrate collision theory, assumes all four conditions. Normally here, what we have given here, the specificity of substrate binding site, this is important for active site, but this is not given in the substrate collision theory. And as we discussed, the lock and key model does not clarify the flexibility, that is, it does not like consist the flexibility of enzyme and substrate. So that is why the substrate will be substrate and enzyme both should be in the flexible in forming the transition state. If they are not able to form, then the product will not be able to form. This is what you also observe in the enzymatic mechanism also. Like in the, when I will be discussing the serine protease reaction, how the serine proteases such as chymotrypsin and lipases do the catalysis. So in that case, the substrate structure need to be modified while being in the transition state. But at the end, this substrate, this transition, at the end, when the substrate and product, when the enzyme and product are released, then the enzyme will come to its native state. But during the transition state, it needs to be reform itself. So therefore, the enzyme need to be flexible, same as the substrate also need to be flexible. Both enzyme substrate are stable with each other. This is also true for the substrate collision theory, and this should have the good molecular orbital interaction. Good molecular orbital interaction means they should be complementary to each other. Now, these are the assumptions of the substrate collision theory in the here, these four, and this is for the active site. When we are dealing with the active site, then only the substrate binding site is the specific to any enzyme. Is it clear? So the correct answer was C. Now the next question is, if the catalysis involves participation of small organic molecules, cofactors, amino acid side chain, and the enzyme, then it is termed as, which will be the correct terminology? Is specific acid-base catalysis, general acid-base catalysis, substrate collision theory, or lock and key model? What will be the correct term for this kind of phenomena? Any guess?
Lock and key model.
Normally here, when you are studying the catalysis, lock and key model and this induced fit model are only for the binding, like how the binding is happening. But it does not term is does not give you any information about the mechanism. Okay, in the question itself, it is talking about the catalysis. So
yes.
both the collision theory and lock and key model are not are out of the option. Now only the specific acid base catalysis and general acid base catalysis are the are in like confusion. So when you have given that there is no specific organic molecules, you have not specified the substrate, then specific acid base catalysis is also not in the option. So it will be a general acid base catalysis that you observe in where do you observe in acid base catalysis? Can you give me any example? Acid base catalysis. The yes.
Proteases work in stomach.
Yeah, very good. That is but which protein?
I mean, pepsin.
Yes, pepsin. Pepsin is there. Yeah, and you already studied in the lecture that lysozyme and ribozyme.
Yes, sir.
Both act as a acid base catalysis. Acid base catalysis means once like in one phase, one particular amino acid will act as an acid and another will act as a base. So these are the general acid base catalysis. Examples are lysozyme and lysozyme and your ribozyme enzyme, ribozyme A or ribonuclease A. Next question is choose the correct option. In the case of positive cooperativity, a small change in ligand concentration give rise to a large change in the concentration of liganded protein. Liganded protein means ligand bound protein, protein ligand complex or enzyme substrate complex. Okay. Statement 2 is in case of negative cooperativity, a large changes in ligand concentration is required to obtain a equivalent changes in the concentration of liganded protein. So answer like options are only one is correct, only two is correct, both are correct, or both are false. What is positive cooperativity? Allosteric activation or allosteric allosteric inhibition?
Allosteric activation.
Very good. And negative cooperativity is just opposite of that, right?
Yes.
So you read both statement carefully and try to understand. So which is true? What occurs in positive cooperativity? Any guess? Okay, let me explain this. Like here in positive cooperativity, which you see in hemoglobin. Okay, hemoglobin structure when it is not, it has four subunit, right? Alpha 1, alpha, alpha 1, alpha 1, alpha alpha, hello, and beta. Yes, yes.
Sir, my voice is not going to you. That's why I
Yeah.
disconnected.
I
Answer
okay,
is only one correct, I think.
Only
one A option is correct.
Only one correct. Okay. Anyone else? And who all are in favor of only one correct? Okay. Yeah, good. So as I was discussing here, in case of hemoglobin, when hemoglobin is not bound to the oxygen molecule, there are a lot of oxygen molecule present. And right now, your concentration of ligand bound means oxygen bound hemoglobin is how much? Very low, which is 0, right? At the time t is equal to 0, when any of the oxygen molecule is not bound to the hemoglobin, then the ligand bound protein, liganded protein means ligand, oxygen bound hemoglobin will be very low. But once this is bound to a one subunit, it will make the conformational changes in the protein, and then it or like rapidly it will enhance the binding of oxygen to the another binding site, and then it it rapidly, like once you do the small changes like in concentration, it will give rise to the large change in concentration of liganded protein. So positive cooperativity does tell about it. So the statement 1 is correct. Now coming back to the statement 2, evaluating the statement 2, negative cooperativity. Negative cooperativity is meant by for comparing the negative cooperativity, you just compare this with the normal case. Okay, cooperativity will only appear when there are more than 2 subunit involved in the binding. If there is only one subunit of the protein, then there will be then you won't see the cooperativity. Cooperativity will arise when you go above 2 subunits in a protein, then only you will see the cooperativity. Okay, so negative cooperativity means you assume another protein which has the 3 subunit, and in the normal case there is a one protein. In the normal case there is no cooperativity, then all of them will bind at their particular rate. Okay, and they will have at time is equal to t, at t time they will have some concentration of C in normal case. But in case of negative cooperativity, you have the same concentration of C, same concentration of ligand molecule. This is protein. This is same protein with cooperativity negative. This is no cooperativity. So and ligand, the same concentration of ligand is given in the both cases. So this will have some protein ligand concentration. To achieve this protein ligand concentration, because this is negative cooperativity, you have to have large change in the ligand concentration, then only you will achieve this PL, this concentration. When you have large changes concentration, then only you will get to this particular concentration. That is what the statement is also tell you, that large change in concentration is required to obtain a equivalent change which is in the normal case to the concentration of liganded protein. So in that scenario, both of the statements are correct. Uh, everyone understood why both the statements are correct, or any confusion?
That means negative cooperativity is also is there.
Yes, negative cooperativity. Negative cooperativity, what will do? Negative cooperativity will stop binding of substrate, binding of this ligand to its protein structure. So if you want to achieve the same concentration, then you have to increase the concentration more and more, right? The ligand concentration in case of protein, in case of negative cooperativity, you have to have very much like like so much concentration of the ligand so that you can achieve this particular concentration. Because what will happen, like if if you have understood the equilibrium concept, if you have understood the equilibrium concept, like if you have less concentration of product in the right hand side and you want to achieve the concentration at your desired space, then what you will do, you will increase the ligand you will increase the substrate concentration. Then the if you have a higher concentration of substrate at equilibrium, if you have highest concentration of substrate in the left hand side, then the reaction will favor in the which direction? Forward direction. Is
Yes,
it
sir.
clear? Yes.
Yes,
So
sir.
to achieve, so in the normal case, the protein plus ligand will give you a some concentration of PL. And in case of negative cooperativity, there will be some another concentration of P-L, which will be lower, obviously lower than this PL, right? Because it is having the negative cooperativity. Then to achieve this one, you have to make a large change in the ligand concentration. Then only you will be able to achieve the same equivalent concentration of this particular protein liganded complex. So that is what the second statement is also talking about, right? So you need a large change. However, in case of positive cooperativity, if you only increase very little bit of concentration of in the normal case, then you will rapidly achieve this protein liganded concentration, because that will enhance the binding of the protein ligand interaction. So both statements are correct here. Is it clear?
Yes, sir, clear.
Okay. Now coming to the next question. This equation represents which kind of inhibition? Quickly. Competitive, mixed, non-competitive or uncompetitive? Any idea? Try to visualize the plot of this equation. Then you will be able to understand it properly, which kind of inhibition it is. So here, what is changing? Vmax is changing or Km is changing? Which one is changing? Normal Magnus Menten kinetics is V is equal to V naught is equal to Vmax into S divided by Km plus S, right? This is the Michaelis-Menten constant equation, kinetics, and you have given this particular equation. So what is changing here? Vmax is changing or Km is changing?
Sir, Km is changing.
Km is changing. It is now alpha Km. This is what alpha is represented, right? Alpha is equal to 1 plus I by Ki.
Yeah.
Okay. Now your Km is changing. If you take the reversal of this equation, 1 by V is equal to Km 1 plus I by Ki plus S divided by Vmax into S, right? So it will give you Km 1 plus I by Ki what a Vmax plus 1 by Vmax, right? Now is intercept changing? Is this in this equation when you are plotting the double reciprocal plot, is Vmax changing? No, right? Only slope is changing.
Km by Vmax.
So which kind of inhibition it will be? Which inhibition? In which kind of inhibition you see the change in Km?
Non-competitive.
Change in Km. Non-competitive. Are you sure?
1 second, sir.
If you plot this, what will be the result? The result will be change in Km, right? So in normal case, let me take another color. Okay. This is without inhibitor. And now with inhibitor, your Vmax is not changing. Means slope 1 by Vmax. This is the 1 by V and this is 1 by S, right? So with inhibitor, what you observe is your Km is changing. So and slope is also increasing. Vmax is not changing and Km is changing. Which kind of inhibition it is? Competitive. Yes. So to attempt this kind of question, try to first do the reciprocal plot and then quickly draw this Lineweaver plot. Then based on the graph, you will be able to understand which kind of inhibition it is. So normally when Km is changing and Vmax is not changing, then this is a competitive inhibition. And competitive inhibitions are reversible inhibition in such a manner, like if you are getting enzyme plus substrate ES complex and then EP. So in competitive inhibition, what you will see, changing like it will inhibitor will inhibit at the only like unbounded enzyme, right? So if you increase the substrate concentration, this will go to the forward direction, right?
Yes, sir.
So that means the Vmax will not change. So if you plot the Maclaurin-Menten plot for this, you will see the
Vmax is
Vmax will be the same, but your slope, your rate will be slower, right? So your rate will be slower, and but you will achieve this at some point of time when you increase the substrate concentration. So in that case, your Km will change, this Km will change, but your Vmax will be the same. That is the competitive inhibition. Now the next question is, in competitive inhibition, what happens to the Vmax and Km if I is equal to Ki? The equation is given here. Now quickly calculate what will be the Vmax and what will be the Km. Quickly calculate and tell me. Equation is already given here in the competitive inhibition.
so since it is competitive inhibition, Vmax will remain unchanged.
Vmax will be
And
unchanged. Okay.
yes, sir. Km will be
And
2 km. 2
Km will
km.
be 2 km.
Yes, sir.
Are you sure?
Yes, sir.
Yeah. So here if you put here I is equal to Ki, that means 1 plus 1, that will be the 2 km, right? So apparent. So alpha is
Correct.
here. Alpha is equal to 1 plus Ki divided by Ki. Alpha is equal to 2. That means the Km will change to 2 km. Right. So your answer will be Vmax is unchanged and Km increases to the 2 km. Okay. So normally this kind of question you see in the like your GATE examination. So try to understand the kinetics, where it is inhibiting in different kinetics, where it is inhibiting, and what kind of fashion it will show in term of Vmax and Km. So the shape and next quick question: the shape geometry complementary is not dependent for the nature of ligand. Is it true or false? Does the shape geometry depend on the nature of ligand? Is it true or false?
Sir, it's false.
It's false because it enzymes also follow what kind of kinetic, what kind of binding? Induced fit binding. So induced fit binding says that the nature of ligand will determine the shape and geometry of the macromolecule. So this is a false statement. Okay. Now for the mixed inhibition. So like you have studied competitive, uncompetitive, and non-competitive, right? What happens in mixed inhibition? So if you change the concentration, like if you change I is equal to Ki, what will be the case of mixed inhibition? What will be the fate of Vm and K, Vmax and Km? So in case of mixed inhibition, your both Vmax and Km will change. Now you can
Yes, sir.
calculate.
Sir, option A is correct.
Vmax lowers to 0.5 and Km lowers to 0.5. Okay. Anyone else? So one vote for option A.
So I think option D is correct.
Option D is correct.
Yes, sir.
Okay, why do you think so?
So on KM value, Vmax will lower. I didn't calculate the Vmax value. I think the KM value will be 2 km here as well. That's
Yes,
why.
very good. Very good. The equation for mixed inhibition is this one. V is equal to Vmax into S divided by, in both of the substrate, mixed inhibition means your substrate is also the inhibitor. Okay. So that you will see in some kind of a reaction where like in some time when you grow your microorganism, you see that term that substrate is also inhibitory to that particular enzyme. Okay, so in that case, what will happen in the normal kinetics? S E plus S will give you the ES complex, and then finally you will get the product. But when you increase the concentration of substrate much higher, then in that case the that what you will see in case of mixed inhibition, what you will see that inhibitor is also inhibiting, and similarly your substrate will also inhibit the enzyme at the higher concentration. So those are termed as the mixed inhibition. So in mixed inhibition, this alpha term will you will see in both of the uh, component. In substrate also alpha S and Km also alpha M. Okay, so here in this kinetics, what you will see, the Km is the Maclaurin constant. Ki is this Ki is the dissociation constant of EI complex. Dissociation constant of EI complex means it is reversing to the backward direction. This is the Ki constant. And Ki dash is the Ki dash is the dissociation constants of ESI complex. Now what will happen? This enzyme plus substrate will also form a ESI complex. The substrate can also bind with the ESI, or here also it can bind. Then the dissociation of ESI constant, the dissociation of ESI complex, either in this direction when it results ES complex or EI complex, this is known as the Ki dash. Dissociation of EI complex known as the Ki, which you see in here. Okay, so now if you put Ki value in both of these, so what will happen? V is equal to Vmax into S divided by Km. This is 1 plus 1, 2 Km and 2 AS. Okay, so how much increase you will see? This is Vmax into S divided by 2 Km plus 2S. Okay, and that you divide by normal Vmax, normal Maclaurin constant. Vmax into S divided by Km plus S. What you will see that your Vmax will be 1/3 of the initial Vmax. Okay, so it will be 0.67. It lowers down to the 0.67 Vmax. 0.67 is the which one? It is 1/3 of the Vmax, and Km is obviously this is increasing to 2 Km. Okay, so what you will see in this plot in like for mixed inhibition, what this is the normal a normal complex. Okay, 1 by V by 1 by S. Take another color. And for the inhibition case, if this is Km, then you are getting 2 Km. This will go to the, because it is inverse, right? So it will go to the lower side and 1 by V will be going up. So the slope will be 1/3 higher, 2 by 3. Okay, so this will be the case of a mixed inhibition. Your Vmax will be lower, means it will go upward direction because both are the double reciprocal plot, and Km will go to the right hand side. You will see this kind of plot. Okay, so now quickly identify these plots. This is for A for this figure A for
Uncompetitive.
which kind of inhibition?
Uncompetitive.
Uncompetitive. This one for
Non-competitive.
and this is for
Competitive.
very good. So A is for uncompetitive, B is for non-competitive, C is for competitive inhibition. Okay, and if you increase the concentration, where will you see your graph going to, in the this side or this side? If you increase the concentration, let us say this is I plus I. Now you increase the concentration plus 2I. Where will you see the graph? Going to the positive direction or negative direction? Which direction?
So I think in non-competitive, the graph will not change due to increasing the substrate concentration.
No. I means not substrate concentration. I am increasing the inhibitor concentration.
Okay, sir.
If you are increasing the inhibitor concentration, where the graph will go? In the anti-clockwise or clockwise?
In the anti-clockwise. Velocity.
Very good. Yes. The Km will be similar in case of non-competitive inhibition. Km will be similar, but the graph will shift to the anti-clockwise direction, and that is true for all cases. Okay. In case of competitive inhibition, if you increase the inhibitor concentration, again the Km will go in the origin side. It will again reduce. The 1 by Km will reduce, means Km is increasing and Vmax is decreasing. Right? Quickly identify this one. What is A? This graph is for
competitive inhibition.
B.
B is non-competitive and C is uncompetitive.
Very good. A is competitive, B is non-competitive, and C is uncompetitive. Now coming to the chymotrypsin catalytic mechanism. Okay, so chymotrypsin catalytic mechanism, this was not taken in the module, so I have taken this because you have studied two kind of catalysis, and both of them were acid-base catalysis. There exists one more catalytic mechanism. There are a lot of catalytic mechanism, but the common mechanism are acid-base catalysis mechanism and then serine protease catalytic mechanism. So serine protease, as the name suggests, in the catalytic residue you will see serine as an active participant. Okay, so in the chymotrypsin, what happens? Like in lysozyme, you saw the catalytic residue that were playing important role, that were glutamic acid 35 and aspartic acid 52, right? Similarly, in chymotrypsin, you will see the role of aspartic acid 102, histidine 57, and serine 195. These three amino acids makes a catalytic triad. These are also called as the serine proteases are also called as the catalytic triad. Okay, so in catalytic triad, these are in the close proximity. This is your serine, because serine has OH group, right? This is your serine. Serine, which one? 195. This is your histidine, histidine 57, and this is your aspartic acid, aspartic acid 102. So what do you see? These are in the close proximity. Now, when here is the base structure from where the all mechanism is happening. So what happens? This histidine is in the close proximity of aspartic acid, and at the optimum pH, aspartic acid will be in the ionized form, right? So this ionization will result in abstracting the hydrogen from histidine residue. Once this histidine residue donates its hydrogen to the aspartic acid, okay, the electron will resettle itself, and then this nitrogen of the histidine will contain a negative charge, a partial negative charge, which helps in abstracting the OH proton of serine. Okay, so what you will see while coming a ester group, acyl containing group, any acyl containing group which have the CO, right? CO group. Now you have generated a nucleophile, because here what will result? It will result you O minus, which is a strong nucleophile. Now this strong nucleophile will attack. Now this strong nucleophile will attack here. Let me take a different color. Now this nucleophile will attack on the CO minus, and you will see a rearrangement happening. Okay. Now once this is a substrate for the serine protease. Substrate, this is a ester, right? Or any protein. Here it is a protein. Protease. Protease means it will cleave the peptide bond, right? So serine protease, this serine will act as a nucleophilic attacker, and it will act on a peptide bond on the carboxylic group, acyl group. So what will happen? This will create a tetrahedral intermediate. Tetrahedral intermediate means carbon having all 4 valencies. Okay. Now what will happen? It will generate a negative charge over here. Now negative charge is generated over the carboxylic ion. This negative charge will be stabilized by the oxyanion hole. Oxyanion hole in chymotrypsin are being formed by the threonine and glutamine, which are the positive charge containing group, right? So they will stabilize this. In the meantime, they will stabilize this negative charge till then, when the again now hydrogen has been absorbed by this, and this is containing the positive charge. Now what will happen? Again the rearrangement will happen, and this negative charge will come and make a double bond. Now during this process, this particular peptide bond will cleave, and it will attach to this particular site for a meantime. And now your enzyme is acylated. Acylated means your serine protease, the serine residue is containing the acyl group. Now your enzyme is modified. Okay. Now it is no more in its initial form, which was this one. So now the enzyme is modified. What will happen now? The first product will release. Means the rest chain will release. Okay. Now now one water molecule hydrolysis will occur. During the hydrolysis, the proton, again, when the charge is stable here, it will generate a negative charge over the nitrogen, partial negative charge, because the hydrogen is accepted. Hydrogen is already accepted by this particular rest of the protein, and it will generate a negative charge over the nitrogen. This lone pair will attack on the like water molecule and it will abstract a proton from here. This phenomena will generate a nucleophile which is OH minus. This phenomena will generate a nucleophile which is OH minus of hydroxyl terminal OH minus, and it will attack on the acylated enzyme, and the same rearrangement will occur. Finally the serine, this bond will break and serine will abstract its oxygen from the water molecule. The OH minus will be attached to the this acylated group and it will release as a second product. This is releasing the carbonic acid, right? And you will again regenerate your enzyme structure, which is here, right? And again the cycle will go on. This this particular group will again come and then the process will again occur and occur. This cycle will go on, and this is how the aspartic acid, histidine, and serine in serine proteases catalyze the process. This is similar to the lipase also. Last time I showed you one Candida antarctica lipase B. Candida antarctica lipase B also falls in serine protease family. The wherever you will see the serine protease family name of any enzyme, you remember this catalytic mechanism. There will be a formation of two tetrahedral intermediate, two acyl enzyme, which is the transition state. Okay, and of this like triad, catalytic triad. In catalytic triad, you will find aspartic acid, histidine, and serine. In some of the case, when serine is replaced by the cysteine residue, then these are called as the cysteine protease. Only in case of serine, you will find cysteine. Is it clear? This mechanism is clear? Serine protease family?
Yes, sir.
Okay. Now, this is the lysozyme catalytic mechanism. Ma'am has already discussed. The first, glutamic acid will act as a acid. The rearrangement will occur. Then it will generate a positive charge on the structure, which will help in abstracting the oxygen like hydrogen from the water molecule. And then in meantime, the aspartic acid will stabilize this charge on this particular like glycosidic bond character. And then finally the oxygen molecule like hydroxyl group of the water will be attached to this neg uh, neg residue. Is it clear? This ma'am has discussed in very detailed manner. So if there are any doubt in this mechanism, you can ask in both of them, ribonuclease A catalytic mechanism or lysozyme catalytic mechanism. Any doubt is there? Both will act as an acid base catalysis. Yes, somebody was talking. Okay, so if this is clear, then the main motto of this of this meeting, which was on week 5, it is complete now. But some of you have interacted me on WhatsApp and asked to clear the three things. One was ionization like ionization pK.
Yes, sir.
Ionization pK. Then the second topic was thermodynamics property, and third was spectroscopic properties. So for ionization, I again, if you are if you are forgetting, I will again reshare that PPT. So which PPT? I think in this PPT I had discussed. Yeah. Is it this slide is visible
Yes, sir.
to everyone? Yeah. Yes. Okay. So let's back to this. Okay. So what happened in like pK value, this ionization thing in your like in your structure when you are in deuterium form, like let's first not talk about the side chain property. Let's first talk about the simple amino acid. In simple amino acid, the C alpha will be attached to carboxylic acid, CO minus, in deuterium form, both NH3 plus, and we are not considering right now the influence of side chain on pK. We are only taking a single amino acid. We are only taking the alpha carboxylic group and alpha amino group. Okay, so this is deuterionic form. Now on like when you are in the deuterionic form, which is deuterium will exist at the pi value, right? When pKa is equal to pi, when pH is equal to pi, you will exist as a deuterium form. Okay, so what will happen when you increase the pH and when you lower down the pH? Right now, your pH is equal to pi. If you are going above your pi, and here your charge is net charge is 0, right? Because negative and positive both are cancelled. So your charge is 0. Okay. Now, if you are going above pH, pH greater than pi, in zone pH greater than pi, what will happen? Your amino group will also lose its proton, right? And then you will have -1 charge. Right? pH greater than pi means your H plus concentration will be lower. So in that case, this H plus will be denoted. This alpha amino group will also donate its proton. So remember one fact that alpha amino group lose its protons higher than the pi value. Means in the basic pH, in the basic condition, the alpha amino group will lose its proton. And in the acidic pH, your acidic pH means the pH lower than pi. The pH lower than the pi, in the acidic pH, both of these will be protonated. And you will see a positive charge on the protein, right? Here it is 0, it is positive, 0, positive, -1. Okay, it is clear. So you calculate the pKa due to this characteristic only. When you see the transition of any protein from +1 to 0 to -1, you take the average of those two pK value. You take the average of those two pK value to calculate the correct pK of that particular amino acid or pi of that particular amino acid. The pi is equal to pKa plus pKb or pK1 or pK2 divided by 2. And this pKa is the pH value where the alpha carboxylic group will lose its proton. At that pH means when you are increasing the pH from left to right, when you are increasing the pH and at the value where the alpha carboxylic group will lose its proton, that will be the pKa value. And when the alpha amino group will lose its proton, that will be its what? pKb value. And you take the average of those two and you will get the pi of that particular protein. Okay, so this was for the simple protein. Now let's take the case of a amino acid which is having another side chain in its like structure. And this is the case of arginine. In arginine, you have positive charge, right? So in case of arginine, at the lower pH, okay, so there will be the two condition at the lower pH. At the lower pH, both will be protonated, right? Everything. In the arginine, you will have carboxylic acid, you will have two amino group. One will be the alpha amino group, another will be the side chain amino group. So at the lower pH, lower pH means the pH lesser than the pKa of alpha amino group. Lesser than the pKa of alpha amino group, the protein will exist in positive 2 charge. Now let's get to the point where this alpha carboxylic first, when you are increasing the pH, which amino group, which group will lose its proton first, amino group or carboxylic group? If you are ranking the losing proton trend, then the first thing that will lose its proton will be the alpha amino group. Okay, so at the pK1 value of the alpha amino group, which is 2.2, at the pH value of this particular amino acid will exist in a like which form? It will exist in a like deprotonated form at higher pH. At the higher, when you are increasing the pH and you are crossing pH of 2.2, then this will exist in a like this form here. Now your carboxylic group in negative charge. Now what is the charge here? In the first case it was positive 2. In the second case it is positive 1, right? Plus 2 and minus 1, which is in the second case after pK1, after pKn it is positive 1, because two ammonia two amino group also have this positive charge. So plus 2 minus 1, which is plus 1. Now which amino group will lose its proton first? Alpha amino group or side chain amino group? So you also remember this fact that if there are two amino group present in the amino acid, one in the alpha amino, one is attached to the alpha carbon, another attached to the side chain, then the first proton, the first amino group that will lose its proton, that will be the alpha amino group. Okay, the amino group which is attached to the alpha carbon. So at the pH 9, the alpha amino group will lose its proton, and then the protein will exist in the net zero charge. Now this is positive and negative. Okay, this is the net zero charge. When you cross pH of 9, now you will exist in a zero charge, net zero charge, and then at the pKa of greater than 10.5, your side chain amino group will also lose its proton, and then you will exist in a what charge? Negative charge. And this is what we have discussed. You have to check where you are getting this transition. Positive to 0 to negative. Okay. So these two it closed. Okay. So these two pKa you will sum up and divide it by 2, and that will give you the correct pKa value. Is it clear? So your arginine are, if you are calculating the value, if you are calculating your if you are calculating the pi value of arginine, which amino which pK value you will take? You will take pi is equal to this one, 9.0 plus 10.5 divided by 2, because these two transition are giving you plus 1 to 0 to -1. Okay, so your pi value will be around 9.8 for arginine, which is true. And this will be opposite in case of uh, a amino acid which is having the acidic charge, like acidic amino group. Okay, so the first, what will happen in case of glutamic acid? What will happen in case of glutamic acid? In the side chain also, or any amino acid which is having the like, there will be 2 NH3 plus at the lower pH. This will be the COOH, and in the side chain you have one more COOH. Okay, so at lower pH everything will be protonated, but when the first thing that will lose its proton, that will be the alpha carboxylic group. Then the second one, why it will lose its proton? Because it is attached to alpha carbon, and now it is having the higher delocalization of electron. So this is the mole polar group. So COOH, the alpha carboxylic group, will lose its proton first. Then in the so then it will exist in which charge? It will exist in the like, this is the negative charge, this is the positive charge. Okay, so it will exist in the look, oh sorry, in the lower pH. In the lower pH, both will be exist in the negative charge. Okay, so at the lower pH you will have -2. Am I correct? No. At the lower pH everything will be protonated. COH alpha carbon. This is NH3 plus. This is R attached to the COH. Okay, so the first thing that will lose its proton, if you increase the pH, the first thing it will lose its proton, that will be the alpha carbon group. Then in that case you will exist in the charge of this is your, right now it is your +1 charge. Now after crossing this, after losing this proton, you will exist in a positive 0 charge, because positive, this is -1, this will exist in a negative, and this is positive. Now you will get the 0 charge. Okay, in the second step, that will be the NH3 plus and CO minus, and your side chain is still having COH. Now in the next phase, this particular will lose its proton. Side chain will lose its proton. It will exert CO minus, and NH3 plus. Now it has how many charge? It will have -1 charge. So for calculating the acidic amino, the pKa value, pi value of acidic amino acid, you will take the first two difference. So it will be in the range of below pH of 5 or below pH of 6. So aspartic acid and glutamic acid both are having the pKa value in below, like in the acidic range. However, in case of positively charged amino acid, you will have the pi value in basic range. Basic range for positively charged amino acid, and for acidic range, like negatively charged amino acid, which are like acidic and basic. So this ionization or calculation of pi value is clear.
Yes, sir.
Okay. Now coming to the like thermodynamic related question. So in the thermodynamic related question, what you will find the questions related to the like you need to remember two equations. Delta G is equal to delta H minus T delta S. This is your first thermodynamic question, first thermodynamic equation, which talks about the change in enthalpy, change in entropy, and change in free energy. Now the another question is related to the equilibrium constant. Okay, why equilibrium constant? When you are studying a reaction, enzyme substrate reaction or protein folding, let's talk about the protein folding only. So in protein folding, what you observe, like you have given a protein P, which is in unfolded state. Now it is going to the folded state. Okay, so from transition unfolding to folded state, you will have this will exist in a equilibrium state. And for if you are writing an equation for equilibrium, then that will be the Kc is equal to, if you are going in the forward direction, means folding state, Fp divided by Up. Okay, this is where your equilibrium constant is. Then your delta G will be RT ln Kc plus delta G free. This is your second equation that you need to remember. So if in the question your enthalpy and entropy is given, then you can calculate the change in free energy using delta G. Or if the concentration is given, then you can calculate the thermodynamic delta G using the concentration of this ln Kc. Free change will be given to you. Then Kc will be equilibrium constant will be this folded state divided by unfolded state, and R is the gas constant, T is the temperature that will be given in the equation question, and delta G if you have to calculate, you can calculate using this equation. Now if this is the only information given and you want to calculate the delta H and delta S, then you first calculate the delta G, then from there you know the temperature, then you can calculate the change in enthalpy and change in entropy. So these kind of problems you get in the thermodynamics, folding and unfolding. Okay, and spectral properties I already discussed while I was talking about this set of problem, this one, fluorescence spectroscopy and UV visual spectroscopy. If you want again explanation about it, so I can give you here. What you will see in UV visual, there are 3 or 4 kind of spectroscopy you will read. One is UV visual spectroscopy. Then you will read fluorescence spectroscopy. Then you will read Fourier transformed spectroscopy, FTIR. Okay, you will read CD spectroscopy.
Yes, sir.
NMR spectroscopy. So these will be the different tools that you will be studying in your analytical chemistry class. Okay, so what are the basic principles about it? So the basic principle behind all of them are based on the electromagnetic spectrum. Okay, so in the electromagnetic spectrum, let me give you that. Let me show you that particular. Okay, I discarded it. That yeah, see. So in this entire electromagnetic spectrum, what you will see that this particular wavelength are the lower wavelength, amplitude is the same. When you increase the wavelength, then this increased wavelength, like how this is happening, like the in your molecule, if there is a atom, okay, atom will have electron, proton, neutrons, right? At the atomic scale, if you are studying a particular nature, okay, so based on the different range of electromagnetic spectrum, the wavelength of the spectromagnetic spectrum can interact differently in the different system. Like how, if you are in the higher range, which is the radio waves, now the radio waves are the much longer wavelength. These are the very long wavelength in the range of 1 centimeter to 100 nanometer, which can travel which can travel to the large distances. Okay, now, and these cannot interact with the matter. But in the IR range, when it is falling from 1000 nanometer to 0.1 centimeter, these kind of wavelength can interact with the bonds that exist in the two molecule. Let us study the CH4. CH4 has four different bonds with carbon, 4 hydrogen attached to the carbon. Now all bonds, when one bond is bonds interaction, like bonds can have vibration. It can go to the different fashion. It can have the rotational motion. It can have the vibrational motion. It can, because bonds are normally represented as a spring. Okay, so it can go to the translation motion. It can compress. It can rotate, rotational motion. So the when you are studying the bond property, like the interaction of light wave with bond, then you are studying the IR, because normally bonds are in the range of in the nanometer range, right? Normally you see the when you the maximum range, sigma bonds are in the sigma bonds are like in the 3 angstrom or 4 angstrom. Hydrogen bonds are being formed. Hydrogen bonds are less than 3 angstrom. So this in the angstrom region, when you study that falls into this particular spectrum in the IR spectrum, and this is the basis of FTIR, Fourier transformed infrared spectroscopy. So in FTIR, you analyze the compound. You on the compound you uh, kind of impart those IR waves, infrared waves, and the bonds in that particular compound can vibrate, rotate, and they can do in the different fashion. And based on the receiving what kind of motion it is forming, based on that you can have the spectral region. Okay, I will show you a template FTIR spectra. See, this is the FTIR spectra. Here the transmittance is noted down on the y-axis, and wave number, which is the inverse of wavelength, is noted down on the x-axis. Okay. So in your compound, which is glucose, you will analyze this kind of spectra. So in the lower, the higher range where the 1400 wave number you are going, these are kind of noisy. Okay, but in the higher range, the different bonds give you the different like peaks. So these peaks, like see here, this narrow peak, which is around 3200 to 3300 wave number, you get that you receive due to the OH, existence of OH. Then in the 2700 region, you see the alkene bond interaction. So this is FTIR spectroscopy. In CD spectroscopy, what you observe, in CD spectroscopy, you see that the let me show you the CD spectroscopy also. In the last class, I showed you the CD spectra, which is the interaction of, normally what do you observe in CD spectroscopy? You kind of impart your like alpha like a structure to a circularly polarized light, and then you notice which direction it is moving. Either it is moving to the like clockwise or anti-clockwise. Based on that, this kind of spectroscopy, based on that you notice the change in angle theta value, which is which is which is observed in the y-axis theta value. Change in the whether it is going to the clockwise direction, anti-clockwise direction, and how much changes the angle of circularly polarized light. So that is being mapped in the CD spectra, and on the x-axis you will see the wavelength. So based on the different interaction, you will find the different characteristic. In the UV spectroscopy, you are studying at the atomic scale, like at the electronic scale, because electrons are making transition. Okay, if only absorption is happening, that you study the UV absorption spectra, and if absorption is coupled with the emission, then that are related to the fluorescence spectra, and that you study in the fluorescence spectroscopy. So that summarizes all three doubts. And if because the time has already been over, so I am not taking much to it. But in the next session, if there are still some doubts are there, then I will take some problem on the next session.
Okay, sir. Thank you, sir.
Welcome. So are there any other doubts related to this week's session or anything?
No, sir.
So if there are no doubt, then we will end the session here. Do give your feedback in the feedback forum in the course portal, and email us any doubt if you have. Okay.
Yes, yes. Thank you, sir.
Thank you for joining, and have a nice day.